Section B, Kepler's laws of planetary motion.
Upon careful observation of planetary motion, scientists realized that the planets have common regularities.
So Johannes Kepler, an astronomer and mathematician, stated these regularities in his laws of planetary motion.
Kepler's first law is that each planet has an elliptical orbit with the Sun at one focus.
An ellipse is a plane figure such that the sum of the distances from any point on the figure to two fixed points in the plane is constant. Each fixed point is called a focus. The longer line segment through the foci is the major axis. Half of that is called the semi-major axis. And perpendicular to the major axis, going through the ellipse's midpoint, is the minor axis. Remember this? Well, Kepler's second law states that an imaginary line that connects the Sun to any planet sweeps out equal areas in equal times.
Kepler's third law, and you'll probably use this a lot, states that the square of the planet's orbital period is proportional to the cube of its semi-major axis.
Remember, we learned about an object's period in the gravity-packed world of physics, Part 1. The period, capital T, is the time it takes for an object to complete one orbit. The period, measured in seconds, is how long it takes for a planet to complete one orbit around the Sun. Or we can use it for any object that orbits around another, like two satellites. So Kepler's third law states that the square of an object's orbit around another object equals a constant times the orbiting object's semi-major axis, cubed. We can write this as an equation where the constant has been found to be 4 pi squared over the gravitational constant times the mass of the body around which the object orbits.
For us, then, t squared equals 4 pi squared over g times m times a cubed, where t is the period of the planet, g is the gravitational constant, m is the mass about which the object orbits, and a is the orbiting object's semi-major axis, or its orbital radius.
Got that? T squared equals 4 pi squared over gm times a cubed. So let's try this baby in a problem.
Titan, a moon of Saturn, has an orbital radius around Saturn of 1.22 times 10 to the 9th meters, and Saturn has a mass of 5.6 times 10 to the 26 kilograms. So how many days does it take for Titan to complete one orbit around Saturn?
First, let's figure out what the question is asking us to find. It's asking us how many days it takes a moon of Saturn, Titan, to complete one orbit around Saturn. Well, that's the period t. Let's look at our equation. We've been given the mass of Saturn, m, and we know the gravitational constant, g, right? And the problem gives us a because that's the orbital radius of Titan, which is also the length of its semi-major axis. So, now we can crank out an answer.
T squared equals 4 pi squared over gm times little a cubed. Filling in our values, we get t squared equals 4 pi, which will approximate as 3.14 squared, over the gravitational constant 6.67 times 10 to the negative 11th newtons, times meters squared, over kilograms squared, times the mass of Saturn, 5.6 times 10 to the 26 kilograms, all times the semi-major axis, 1.22 times 10 to the 9th meters, cubed. Now, let's do the numbers, then figure out the units. Starting over here and cubing 1.22 times 10 to the 9th, we get 1.82 times 10 to the 27th. Now, squaring 3.14 in the numerator and multiplying by 4, we get 39.4. Multiplying this by the number we just got on the outside, we get 71.71 times 10 to the 27th. In the denominator, 6.67 times 10 to the negative 11th times 5.6 times 10 to the 26th is 37.35 times 10 to the 15th. Dividing these two answers, we get that t squared equals 1.92 times 10 to the 12th. Okay, how about the units? Well, we have meters cubed over newtons times meters squared over kilograms squared times kilograms. Converting newtons to kilogram meters over seconds squared, we can start canceling things out. The meters all cancel out, as well as the kilograms, so we just have 1 over seconds squared in the denominator, which flips over to leave us with seconds squared as the unit for our answer. Now, we're not quite done because this is t squared, and we're looking for t. So taking the square root, we get 1.39 times 10 to the 6th seconds. So Titan's period is 1.39 times 10 to the 6th seconds.
Now, if you're not sure if you set up the equation properly, one way to check is if you look at the units. If the units cancel out and you end up with just seconds, you did it right.
But wait, we're not done yet. We just found out Titan's period, 1.39 times 10 to the 6th seconds. But the problem asks for us to find Titan's period in days.
Okay, we know that Titan's period is 1.39 times 10 to the 6th seconds. There are 60 seconds in 1 minute, 60 minutes in 1 hour, and 24 hours in 1 day. So, in order to convert 1.39 times 10 to the 6th seconds into days, multiply by all the ratios, and we get 16.1 days.
So it takes Titan 16.1 days to make one orbit around Saturn.
To watch more free educational videos, visit our website, studioforlearning.tv. Stretch your brain online.